Okay, I had mentioned in class the geometric sequence is such an important sequence that we study in calculus, and I just want to make sure that we understand the formation of the sequence. So each term in the sequence is found by multiplying a previous term by a fixed constant called r, which is the ratio. So the sequence is going to look like r to the n. This is the general form. Or it could look like AR to the n, where the ratio and A are real numbers. So for example, if you have a sequence that looks like this, right, that would be dubbed a geometric sequence, with R equaling 1.3. Now, the behavior of the sequence, as far as whether it converges or diverges, is going to be solely dependent upon this ratio. So the limit, as n approaches infinity, of the sequence, r to the n, if r is between 1 and negative 1, let me rewrite that a little better. So if r is between 1 and negative 1, then the sequence is going to converge to 0. It converges to 0. If r is equal to 1, it converges to 1. And unfortunately, right, if it's outside of this range, so if r is less than or equal to negative 1, or r is greater than 1, it's going to diverge. The limit does not exist. Okay, so let's do an example. I'm going to pause here. Okay, we'll do two quick examples. We're going to look at the sequence, determine whether it converges or diverges, and then we're going to state whether it does so either monotonically or by oscillation. And if it does converge, give the limit. So let's look at the first one. So the geometric series 0.2 raised to the nth power. If I expand this series, and you should, just to see what's going on, and I follow the series out, oops, got one too many zero there. Oh, pause. The perils of making a video at home. Okay, so the next term in that sequence looks like that. So the sequence, because r is between 1 and negative 1, and it's 0.2, it converges, and it converges specifically to 0. So it converges to 0. It's monotonic, because it's non-increasing. It's also bounded, where the upper bound is equal to 0.2, and the lower bound, since it converges, is 0. Okay, so that's one example. Let's do another quick one, and then that'll be it for this, and we'll do a warm-up tomorrow. Let me look at a different one. So if we have the series, another example, negative 0.25, let me rewrite this, negative 2.5 to the n. So looking at this sequence and expanding it, right, you see, hopefully you notice that this thing is going to diverge. It's going to get bigger and bigger and bigger, right? And let me find the first few terms. Let me pause to find the first few terms for you. Okay, so the expansion of that series, the first 4 terms look like that. So hopefully you notice that this is diverging. Specifically, it diverges because r, right, is less than are equal to -1. So it does diverge, and it diverges by oscillation. Right? It's bouncing around on the negative and the positive sign, right? So it's diverging by oscillation. Okay, we'll pick up here tomorrow.